IV 2012 conference. Our first session is called Driver Assistance Systems, number 1. And we have 4 different talks this morning, each one about 20 minutes. All the speakers have checked in except for the second one. So again, wanted to ask the audience real quick. Nicholas Hoch, if you're in, we'd like to have you check in and make sure that you have your computer ready. But anyway, my name is Matt Barth. I'm with the University of California, Riverside, and I'll be chairing the session. And I think just to keep on schedule, we're going to go ahead and get started. So our first speaker is Stephanie Lefebvre, and she's going to talk about risk assessment at road intersections, comparing intention and expectation. So Stephanie.
Thank you. Hello. So I'm Stephanie Lefebvre, and indeed I'm going to talk about risk assessment at road intersections. First of all, I'd like to point out that intersection safety is still a major challenge, both for driver assistance systems and for autonomous cars. Between 40 and 60% of accidents happen at intersections in most countries, and during the DARPA Urban Challenge, 5 accidents out of 7 happened at intersections. Now, if we look at the standard approach for risk assessment, it consists in using a motion model to predict all the potential trajectories of the vehicles in the scene, and then check whether or not these trajectories will collide. And in general, it is assumed that vehicles move independently from each other. This is done for complexity reasons, because at intersections, you can have a high density of vehicles. There are many different maneuvers that the cars can perform, and the dynamics of intersection situations can get quite complex. However, there are some drawbacks with the independence assumption, both for how well you can estimate the intentions of drivers and also for risk assessment. So in one example is you will not be able to correctly interpret situations where one vehicle is yielding to another one. And for risk assessment, there's a tendency to overestimate the risk with the independent assumption. And in this work, we propose a novel approach to risk assessment at road intersections. And instead of predicting the trajectories and checking whether or not they collide, we propose to detect dangerous situations by comparing what drivers intend to do with what they are expected to do. And one advantage of the approach is that it takes into account the mutual influences between the vehicle's maneuvers. The implementation is done in a probabilistic manner. We use dynamic Bayesian networks. The intention is estimated from the motion of the vehicles, so from their successive position, orientation, and speed. The expectation is derived from the intentions of all the drivers in the scene and combined with the traffic rules. As for the risk, we compute it based on the comparison between intention and expectation. Inference is performed with a particle filter in this work. For representing an intersection, we take into account the fact that intersections are highly structured environments. So for every possible maneuver at the intersection, we define an exemplar path, which in this case consists of a set of interconnected nodes. And at this intersection here, for example, you have 6 different possible maneuvers, so we have 6 exemplar paths. So now I'm going to describe the dynamic Bayesian network, starting with the variables. In this work, the variables that we observe are the position, heading, and speed of all the vehicles. Then we define some higher level behavioral variables, which are hidden. So we define the maneuver intention of a driver, which means which of these maneuvers the driver intends to perform. We define the distance traveled on this maneuver, and we define whether or not the driver intends to stop at the intersection. We also define an expectation variable, which is also hidden, and which corresponds to the necessity for the driver to stop at the intersection. Now, this is the graphical representation for our model, and it should be interpreted as follows. The expectation for a vehicle N at time t is derived from the previous behavior and physical state of all the vehicles in the scene. So when you see thick arrows here, they correspond to multi-vehicle dependencies. then we assume that the behavior of a car at time t depends both on the previous behavior of the car and also on the, what is currently expected of the driver. And since the expectation depends on all the other vehicles, this means that the behavior of a car at time t will be dependent of all the other vehicles in the scene. And this is where we model the influences between the vehicles' maneuvers. And finally, we assume that the physical state of a vehicle depends both on its previous physical state and on the current behavior of the vehicle. I will go now over the parametric forms. For the pose, we assume a normal distribution, and we use the exemplar path to compute the probability of a certain pose, given the maneuver intention and the distance traveled. For the evolution of the speed and of the distance, we use some typical speed profiles of drivers at intersections. And for the maneuver intention, we simply assume continuity in the intention. For the expectation to stop, we define a function which combines the traffic rules and some probabilistic gap acceptance models that we found in the literature. To illustrate this function, I will use a simple example. So here we have a vehicle V which is reaching a giveaway intersection. And there are two priority cars driving on the main road. And we want to compute the probability that this car should stop at the intersection. The first step is to project forward the scene until the car reaches the intersection. Then we compute the time gap available for this car to execute its maneuver. And as you can see in this example, the time gap is very short because of this black vehicle here. And finally, we compute the probability that this time gap is sufficient to execute the maneuver. For this, we use some probabilistic gap acceptance models. And as you can see in this situation, the gap is probably not sufficient. And this means that the probability that this car is expected to stop will be very high. And finally, for the intention to stop, we use a compliant driver model. We say that if the driver intended to stop at the previous time step, and if he's currently expected to stop, he will probably stop. If the driver didn't intend to stop, but he's not expected to stop anyway, he will probably not stop. And then if the previous intention and the current expectation do not match, we don't assume anything about the driver's intention, so we use a uniform distribution. The computation of the risk is based on the probability that the driver is expected to stop and he does not intend to stop. All the computations will be based on this term. And this has a variety of applications. One of them is the detection of hazardous vehicles. Another one is the computation of the risk of a maneuver, which is of particular interest for autonomous driving. The algorithm was tested during field trials. We equipped 2 passenger cars with vehicle-to-vehicle communication modems. So the cars shared their position, heading, and speed information at 10 Hertz. And the reason why we use vehicle-to-vehicle communication and not other sensors like cameras or lasers or radars is because this way we don't suffer from the field of view limitation of the sensors. And therefore we can run tests on blind intersections like this one. The application that was tested is the detection of hazardous vehicles. So the system triggers a warning when it detects that there exists a vehicle for which the probability that the driver is expected to stop, but he doesn't intend to stop, is higher than the threshold. This was tested on 2 scenarios, with a priority vehicle driving on the main road. And in the first scenario, the violator vehicle violates the priority while emerging in the intersection. In the second scenario, he violates the priority while making a left turn across path. We have 90 instances of these tests, which were obtained from 6 different drivers. And every time in these tests, the warning was triggered early enough that the accident was avoided with emergency braking. In the next slide, I'm going to show you a video which was recorded in the cars for this scenario. So this is me driving in the priority vehicle. I'm on the main road and I'm approaching an intersection for which I have priority. And this is the view from the violator vehicle. So the vehicle is approaching the same intersection from a smaller road, and as you can see here, this is a giveaway sign, so the driver is supposed to stop, yield, so wait for me to pass before he executes a left turn. Except, as you can see on the image, this is a blind intersection, so the driver cannot see me. And what will happen is the car will proceed in the intersection, make a left turn without waiting for me to pass. So the system detects that there's a dangerous situation, and I get a warning telling me that there's danger coming from the left. I apply emergency braking, and the accident is avoided thanks to this. I will replay it just once, just to explain that it's hard to see on the video, but this was actual emergency braking. Without the hard braking, there would have been a collision. And if you look at when the warning was triggered, you can see that we get the warning when the drivers cannot yet see each other. And this is possible thanks to the vehicle-to-vehicle communication. We also ran some experiments in simulation so that we could have some collisions. We have tested 4 scenarios, and we have 320 instances of these scenarios, which were obtained by varying the speeds of the vehicles and by alternating between stop violations and priority violations. So a stop violation means that the violator vehicle doesn't even stop at the intersection, whereas a priority violation means the violator vehicle stopped, but then entered the intersection when he should have waited for the priority vehicle to pass. So this graph shows the percentage of detected collision as a function of the time remaining before the collision. And as you can see, there's a difference between stop violations and priority violations. On average, there's a 1 second difference in detection time. For priority violations, we are able to detect 100% of the collisions 1 second before they occur. For stop violations, we detect 100% of the collisions 2 seconds before they occur. Now we can move a bit further and analyze the percentage of avoided accidents depending on which strategy we use after we detect danger. And here we tried 4 different strategies. We tried auto brake on the violator vehicle, warning the driver of the violator vehicle, auto brake on the priority vehicle, and warning the driver of the priority vehicle. And we found that the numbers vary a lot. I'll take one example. In the case of priority violations, if we apply auto braking on the violator vehicle as soon as we detect that there's a danger, we are able to avoid 98% of the accidents. Whereas if in the same situations we warn the driver of the priority vehicle, we avoid only 3% of the accidents. And the reason is actually quite easy to understand. It's because in the priority violation scenarios, the violator vehicle is driving really slowly. So if you apply auto braking as soon as you detect the danger, the vehicle will be stopped almost immediately and you can avoid most of the accidents. Whereas if you warn the driver of the priority vehicle, first of all, there's driver reaction time that slows things a bit, well, a lot actually. And also the priority vehicle drives very fast because it has priority. So by the time the car will come to a complete stop, we can see that most of the time it's too late and we cannot avoid the accident. As a conclusion, we proposed a novel approach to risk assessment at road intersections. Instead of predicting the future trajectories and checking whether or not they collide, we propose to detect dangerous situations by comparing what drivers intend to do with what they are expected to do. Both the intention and the expectation are estimated in a probabilistic manner from the successive observations on the vehicles and also taking into account the traffic rules. The method accounts for the mutual influences between the vehicles. The results during the field trials proved that we can do risk assessment in real time in passenger vehicles. And the results in simulation showed the importance of selecting the right avoidance strategy once we detected danger. For future work, we would like to do more testing on intersections with different geometries, with more cars, We would also like to add some sensor data fusion so that we have a more comprehensive representation of the situation. In particular, we would like to add pedestrians to the model. And finally, we would like to try this approach for applications which concern computer-controlled vehicles. This is the end of my talk. Thanks for your attention, and I'll be happy to answer questions.
Do you have time for a few questions? Questions? Right down here. I think the microphones are coming around right behind you.
Well, the question is, when you have, say, no right-of-way regulation, so like a four-way stop, and the expectations are pretty much the same. What the system do?
You mean for stop compared to give-way intersections? Is this the question? What do we do when we have a stop intersection?
With a four-way stop, everybody has to stop, okay?
Yes.
Now, at the time, of course, it's well understood that normally in practice, just one of the four guys would go. But the system is giving some advice what to do. And by the way, if there are some two choleric people among the four drivers, maybe even two would try to go. So what would the system do?
I'm sorry, I cannot hear you. I'm sorry, I cannot hear you very clearly. What would the system do in the case of a four-way stop intersection?
Yeah. In all these cases where the expectations don't give a clear answer what to do, the expectation evaluation.
Everything is probabilistic, so the expectation to stop when you're approaching the intersection will be 0.99999 because you should stop anyway. And then when the system detects that the vehicle has stopped, then depending on the presence of other vehicles and who got there first, you have a probability that you're expected to stop for all the cars.
It's not an answer, but we talked privately, I think. Thank you.
Great. Other questions? Right down here.
You showed that the main benefit in collision avoidance was on the violating car in terms of avoiding crashes. But if you would, have you done anything in accidentology comparing the benefits of braking, but where the collision would not be avoided, but you would still have substantial benefits in terms of fatality and injury reduction? Is the conclusion the same? It's that the violator car is still the most important?
So I haven't done studies on how well we are able to mitigate accidents, mitigate the results of accidents. I would expect the same results because in any case, the fact that the priority vehicle drives faster means it will take longer for the car to stop. So I would expect the same results, but I haven't run these studies.
Okay, we have time for one last question, if anyone else has a question. If not, I have a very brief question myself. So you heard in the very first keynote talk today that even though we have traffic rules and that can serve as the basis for expectation, often is the case where those traffic rules are often bent by the drivers. And so in your model, do you have a way of learning that or understanding it besides just using the traffic laws themselves, the traffic rules?
So we don't do any learning, but for example, the probabilistic gap acceptance models that we use to say whether or not a driver has time to merge into the intersection, for example, these are based on real data. So they're statistics on what people consider a safe merging to be. So we don't have learning, but these statistics on what is expected are actually, they're probabilistic and based on real data. Because like you said, there's no exact calculation of who should go first, and things are not always clear. You need probabilities.
Great, okay. Well, let's thank the speaker again. Thank you. Okay, our second speaker is from Volkswagen, and I think they're coming up. So Nicholas, right?
Yes.
Okay. So our second speaker is Nicholas Hoch. He's from Volkswagen in Zurich, and he's going to talk to us about electric vehicle travel optimization, looking at customer satisfaction despite resource constraints.
So welcome to my talk. Oh, it doesn't work.
It's on these screens, but there we go.
Okay. So welcome to my talk, Electric Vehicle Travel Optimization, Customer Satisfaction Despite Resource Constraints. Please let me just draw the bigger picture first. Just a little excursion. You probably all have petrol cars. You probably have experienced that refueling with petrol cars doesn't really hurt your time schedule. Depending on where you live, you've probably had problems with traffic, probably not. Same with parking search traffic. You might have been searching for parking places, maybe not. But anyway, your customer expectations have been built in times where resources were cheap and available. And your customer expectations will grow in the future, so you will expect more. However, resources become less and more expensive. So the major challenge is basically how to make more from less. And how does actually my presentation blend in there? So we have the customer expectations from basically petrol vehicles. And then we have electric vehicles, which have completely different properties. They have less range, they have longer charging times. Then in future, we'll have an infrastructure with less parking, with higher traffic density. So there's less resources, and we try to optimize the customer's travel pattern, I'd say, so that this customer expectations are satisfied despite the constraints. So as an introduction, the situation is the user has limited knowledge of vehicle characteristics and infrastructure availability. The user requires carefree travel and at reduced cognitive load. However, on the right in the picture you see it's not really so easy. You have lots of vehicles, you have vehicles interacting with each other, like vehicle-to-vehicle communication, vehicles with infrastructure, you have parking lots, charging stations, you have ICT, and then you have the user and its timetable. So the complication here, the particular complication is it's very highly connected, and then additionally, the electric vehicle is very highly connected. So energy consumption and travel time really depend on each other, and the characteristic of dependence is different from petrol vehicles. Then energy intake, charging time, charging cost, they're all mutually dependent. Moreover, time-dependent availability of infrastructure resources like traffic, parking lots, and charging stations. So basically, if you're the user, you don't want to end up at a charging station that you planned, which is then not available. So then you really have a problem. And then you don't know when will there be a charging station, at what time that is available. How should I plan then my trip in order to get there in time with the right amount of energy? So that's really complicated, and that's exactly what we address in this approach. So this is a little problem description, basically putting into an example what was stated before. Look here, you have on the y-axis, you have the vehicle state of charge, the minimum battery level, the maximum battery level. Then you have on the x-axis time. Then in between you see those like gray boxes. You have GF for Gifhorn. This is all 3 towns in the north of Germany. You have WOB, which is Wolfsburg, and BS, which is Braunschweig. They're all like 20 to 30 kilometers apart. So you have some user starting at Gifhorn. Now there are different options to travel to Wolfsburg. You can either take a very, very fast road, which would be the D13 with a very high energy consumption. I must say it's all linearized, so in reality it's more complex. Then you have the D12 option, which is like medium travel time, medium energy consumption, and the D11 option, which is higher travel time and less consumption. So then once you've arrived in Wolfsburg, you have different options. You either arrive at a car park and you can't charge, or at a charging station, and there are different modes. So you can have a fast charging with very high energy intake at high cost, or low energy intake at lower cost. So this is the C1 to C4 options. Then your choice you've made, and the choice is visualized by the dark line, your choice you've made has an influence on the consecutive choices, or on the consecutive choice set. So if you've chosen D12 and then not charged, so C4, your choice is limited. So the option D23 going to Braunschweig is not feasible anymore due to energy constraints. The option D21 is not feasible due to time limitations, so you wouldn't arrive in time. So you're left with the option D22. So this is a very, very simple example. Making this more general, it's like what the travel optimization should do is it should invest time where energy is critical. It should save time where energy is not so critical. It should charge so that it blends in with the user schedule, its appointments, for example. And the combination of individual decisions should fulfill the resource constraints and the user preferences. So, our approach. We divided the whole problem because it's a very complex problem in different levels. So we have down the bottom, we have the component level. There we consider the user, its preferences, its travel pattern. We consider the vehicle with all the intercomponents, like the subcomponents, air conditioning, infotainment system, lots of auxiliary consumers, and of course the drivetrain. Then we have charging stations and parking lots. We have an availability monitoring, like a booking monitoring, and all that stuff. So we have a model for each component. Then we use these models on the trip level. A trip level is one starting location, one destination location. Around the starting location, you have different parking lots or charging stations. And around the destination location, you have different parking lots and charging stations. So your trip is multimodal. It's a walk to a parking station, it's a drive to the next parking lot, and it's a walk to the destination. So now you have the complexity is basically all the, say, mutual pairs or all the pairwise combinations of origin parking lots and destination parking lots and charging stations. In between each pair, you can have different routes, different driving behavior, different traffic conditions. So this trip level, we now combine to the and put it into the journey level context. So on the journey level, you have different trips connected. And as we've seen before, the decision you make on one trip has influences on the choice set of the others. Then the mobility level, I just probably 2 sentences there because it's not treated in this paper. We do not consider vehicles and user connected anymore. So if we say we don't have one user and its private vehicle, but multiple users and vehicles like car sharing, carpooling, ride sharing, then we can disconnect them. And so this will open up our choice set even more. So now going to the method. You see on the left the little figure there, the user, the vehicle, and down there like parking charging, it's like a representative for infrastructure resources. You have the vehicle and the user connected throughout the driving phase. Then they separate. The user walks to the appointment, walks back. So appointment is like anything, some activity. While the user is walking, having the appointment, walking back, the vehicle is at the charging station or parking lot. So either you fully charge the whole time, or you charge in intervals, which is vehicle to grid, or you don't charge, which is just a parking lot. Of course, when you want to stand there, it has to be available. So down the infrastructure, you have a charging station and car park availability, which is a necessary requirement. So this we were formulating, and then we're formulating some constraints to the optimization problem, which is user satisfaction of user appointment times. So we never should run late. Probably a very German thing, but anyway. EV state of charge limits, so we never must underrun the battery limits, of course. Then maximum user walking distance, so if the user requires not to walk more than 1 kilometer to the destination, that should be respected. If it's a disabled person saying, I want a disabled car park not further away than 20 meters, that should be respected if possible. Then traffic, of course, we can't go faster than traffic. Even VW can't. And parking lot and charging station availability, of course, we can only park if it's available. So, so method 3, it's the cost criteria. On the trip level, we are weighing consumed energy and travel time. On the journey level, we additionally weigh charging cost, number of charging events, waiting time, walking distance, and final state of charge. The cost function is of the form shown down there. It has a constant term, alpha, and a function, which is continuous and continuously increasing, monotonically increasing. And then, of course, the cost function criteria mentioned above. So the function, you may either set it to the identity function, or you can, if you say, yeah, I don't want to have a too strong penalty for time, like of a deviation of 5 to 10 minutes, then it can have sort of a weak penalty there, and then grows whatever, like according to the function later. So you can penalize time deviations above 10 minutes, for example, very strongly. So going to the results. So we basically implemented a whole method, like we implemented the routing, time energy optimal routing, we implemented the whole modeling, the temporal modeling, we included real customer preferences, and finally we came up with some results. So the results section I want to divide into 2 phases. One is the specific case, where we just have one travel pattern for one user and its specific preferences. You have the travel pattern there on the left, Wolfsburg, Gifhorn, Wolfsburg, Braunschweig, Wolfsburg, which is a very common journey. And then preference set, energy consumption, travel time, charging cost, and the number of charging events. That's what the customer wants to have weighed or prioritized. Then on the right, you see the comparison of the best versus the worst feasible journey. I must say it's feasible journeys, so they all work. So they might be journeys the user really travels. So there you can see you have different departure times, you have faster routes at higher energy consumption, you have different arrival times, of course. Then the worst journey charges at the Wolfsburg location, goes very fast again, and charges again at the Braunschweig location, which of course involves different cost. And then you see the best journey according to the preference set in light gray. So this just shows that within the set of feasible alternatives, there's quite a potential to match preferences of the user. So putting this sort of to the general case, for different routes, different users, it's sort of an intersection of a great variety of users. We showed on the trip level and on the journey level what the improvement potential is. And you can see that duration and energy consumption, so travel time and energy consumption, can be mostly influenced on the trip level. You don't have really lots of improvement potential on the journey level, because on the journey level you can't really influence the route choice, you can't really influence the driving style, you have no control over traffic. That's all evaluated on the trip level. And the trip level alternatives then are passed on to the journey level, where you can see there that on the journey level you can majorly influence charging cost and energy, which we refer to the energy you have at the final appointment or at some specified appointment. So if you don't know what you're doing afterwards, you can say, I want to have a fully charged battery, so I'm sure. So these 2 cost criteria you can influence on the journey level, you can basically determine on the journey level your charging strategy and your cost strategy. And as you can see, the potential, the improvement potential is quite significant, so that such a planning approach in the end will probably satisfy quite a great variety of users. And lastly, and then I get to a short summary, having electric vehicles, which is like a new type of vehicle, involves lots of anxiety. So if you can show such things, and you can show that you eventually can guarantee reaching your destinations, and you can guarantee a certain level of preference satisfaction, users will be much more likely to jump into that technology. So finally, the summary. The challenge was conflicting resource requirements from the user, the infrastructure, and the electric vehicle. The objective, of course, is the customer satisfaction despite resource constraints. The approach was through coordination, we resolved that resource conflict. And the method was we're implementing on the trip level time energy optimal routing. We're evaluating these routes under consideration of user travel patterns, travel preferences, and parking lot availability in the journey level. And lastly, we are evaluating charging strategies, parking strategies, and cost strategies also on the journey level. So come to the end here. Thanks very much for your attention, and I'm open for questions now. Thank you.
Questions for the speaker? There's one right down here.
Okay,
Oh.
your work is very interesting, but my question is that is this feasible to set up a kind of cloud server to help more people to arrange their trip? For example, as far as I know, for example, like the traffic light, there are somehow kind of cloud algorithms to calculate the optimal result of the traffic light. But based on your work, is this feasible to set up such a kind of the cloud server to help more people? Or what's the challenge of that?
I'm not quite sure whether I got the question. Is it? I got there. One thing I guess was how influence, like stochastic influences on the road, like traffic lights, are incorporated into the model. Was that one question? Yeah.
For example, in a local area, a lot of people must arrange their trip. And is that feasible for just directly implement based on your work, or what's the challenge of that?
I mean, I'm not quite sure again.
Sorry, maybe I can explain more details. For example, your work is for the individual persons to arrange the trip. My question is that for a lot of people.
Okay, wonderful, yeah. Yes, you're completely right. If you have the same strategy for all people, then of course the global solution, because we have to differentiate two perspectives, the local perspective and the global perspective. And if we have the same strategy for everyone, of course the global perspective will deteriorate as well as then the local perspective. So for a certain penetration rate, that works very well. But if you increase the penetration rate, it gets worse, of course. And that's some future work that has to be performed. What charging strategies and what planning strategies, moreover, really solve this global-local issue? Which strategies, or even distributed strategies, or completely different, or you probably just change cost functions or whatever, which strategy in the end guarantees that the local perspective is satisfied, while the global perspective is also improved, or at least not deteriorated? Did that answer your question?
Okay, we have time for one very short question. I know we had one right down here. I don't know if a microphone's coming. You want to just speak loudly real quickly, and then we'll...
We can exchange microphones.
In a way, what you have been talking to us methodologically, that is multi-criteria decision-making, as you know. And at the same time, applied to this electric car problem, there is no problem so far just because there are enough electric cars. But if you have more, and you don't have a kind of safe way to globally deal with the situation, from your standpoint, I don't see whether you can avoid a complete collapse of a car or of a jam, of a congestion of electric cars, which is of course very hard to solve because they cannot charge in the meantime.
Yes, I mean, of course I presented it for electric vehicles, but in the end it's not really so different from what we have today. I mean, we have constrained roads basically. There's only a certain throughput and there's a certain number of cars going through. So even petrol cars. So now we have navigation systems, which is some sort of planning. And so you could argue if everyone has a navigation system, which is state of the art now, and with a high number of vehicles and the roads, you'll have a collapse. And you do sometimes. And that's what they have been investigating, how the strategies on the navigation systems could actually be changed or varied so that this collapse doesn't occur. Now with electric vehicles, you're completely right, we have the same situation just with less resources. At the moment we're lucky because we don't have the vehicles, but then once the vehicles are there, we have very little charging resources for the vehicles. So it's a similar situation. There might be collapse. However, using intelligent coordination techniques will at least reduce the collapse, if not even solve it at some stage.
Great. Okay. Well, let's thank the speaker again. Thank you very much. Okay, our third speaker of the session is Cristobal Curio, and he's going to talk about detectability prediction and dynamic scenes for enhanced environmental perception. So we're going to switch over computers and get started.
So, welcome to this talk. I'm presenting work of my former student, David Engel, who is now at MIT. My name is Cristobal Curio. I'm heading the Cognitive Engineering Group in the Max Planck Institute for Biological Cybernetics in Tübingen, Germany. So, imagine you're driving to work, you're doing everything else than paying attention to the road, and suddenly you have to look up. And this is actually what this is about. You look up and you have to really make a fast decision while the scene is dynamically evolving over time. And these few milliseconds is actually what we are approaching in our computational and psychophysical approach that I'm going to present you here now. You probably all agree that things drivers are still better at than computers or driver assistance system is decision making, with a constraint that if the driver knew all the factors. And I'm especially focusing here on the visual factors in the talk. So an area of research that has been long promoted now for a long time is the interface of biological vision and artificial vision. And it just in the last few years that this area is actually looking promising. Just imagine, and it's more interesting actually that neuroscience or psychophysical experiments can actually lead you to new developments in technical driver assistance systems. So we wanted to operationalize this somehow very promising direction by looking at the task of pedestrian detection. So you're mostly experts probably more in this area. I just listed a few themes here You use sensors, raw image data, you extract features, you do classification, object tracking, you design co-drivers that introduce probably automatic braking behaviors, and you visualize information that hopefully is helpful to the driver in an alert and hazard situation. In parallel, cognitive science looks at retinal images and these full list here of, for example, attention, eye gaze, active vision, adaptive vision, risk estimation, decisions, driving, but all these themes are looked at not coherently yet. And to bridge actually for purposeful driver assistance systems these two areas, this is largely unknown how to do this. Can we maybe bypass this whole loop here? And I want to suggest a solution that actually hinges in at these bottom layers, at the lower feature level layers of a scene where we can actually do helpful improvements that could enhance the driver's perception during alert situations. For this, last year we have introduced the concept of pedestrian detectability at the Intelligent Vehicle Symposium in Baden-Baden. It is defined as a probability that a pedestrian will be noticed by a driver at a glance. To connect machine vision and human vision purposefully, we learned the relationship of some scene properties and the human ability to detect the pedestrians. Human gaze, naturally, as most of you assume, is the dependent factor that we seek to optimize with our computational approach. So we provided a proof of concept for static urban scenes and desperately needed, and everybody asked, is this also valid for more ecologically relevant scenes, dynamic scenes evolving over time and situations? This is what we actually want to present here today. So what factors actually might determine the detectabilities of pedestrians in the scene? This is a nice example, and I browsed through a few snapshots here. So if you look at this pedestrian, it might not be so well detected because it's embedded with its local appearance within its surrounding environment. So it might be less easy to detect this pedestrian. This pedestrian might be noticed at a glance by the driver quite easy since it's currently moving, and maybe even more easily this pedestrian might be detected at a glance because the contrast is quite high with respect to the background. So you imagine that probably an automatic system should guide the attention of the driver at a glance more to such points, to areas where the pedestrian is less likely to be detected. So this the detectability function which we are aiming for is a sum of many factors, geometric relationships, and local visible factors that we are able to measure with computer vision, and that we would like to plug in this predictor function in order to optimize the gaze of a human observer, the driver in this case. So what we exploited here are available databases, dynamic databases, provided, for example, here by Caltech. There are other databases available, but this database fitted mostly our needs to design this experiment. So we have a lot of data. We have bounding boxes with two types, manually labeled, partially observable parts of pedestrians are differently labeled than fully observable pedestrians. For our experiments, we prepared and selected subsequences of these databases that we let subjects look at in our experiments, which I'm going to outline in a second. So we selected subsequences of 2 to 5 seconds. We sorted these sequences according to the population size present in these sequences at the last frame, ranging from 2 to 7 pedestrians. And we tried manually by sorting out visually similarly looking scenes. So in order to determine these detectabilities, which we are aiming for automatic prediction, I want to introduce the following protocol. The driver is distracted while he is performing the secondary task here. Peripherically, he could observe this blurred scene on the left side. And the task of the driver was to keep with his mouse buttons this is a circle in the middle of this display. So this is something like a proxy task for example, manipulating a radio station. So it's the next time we randomly draw the attention of the driver with a fixation cross to such a location and briefly post him for a few milliseconds with the real environment. Right after, we had the response phase. Subject had to indicate by memory, by a proposal of suggesting and ecologically relevant realistic bounding boxes distributed naturally over the scene. They had to indicate it, here indicated by green boxes, where they memorized or have seen a pedestrian. As such, that's led to these detectability numbers. For each trial and labeled pedestrian, we obtain a sampled knowledge about the ease of the detection of these pedestrians with respect to this fixation cross, a number. Now, we wondered what features in the scene might be responsible, what are the critical features that allows us to predict these detectabilities in the scene in order to automatically optimize these point of fixation points where we optimize this number. As you expect, we have distances like the pedestrian of a hypothesis, the hypothesis of a pedestrian to the middle of the visual field, distances of likely fixation crosses to the pedestrian, the local contrast, as you imagine, of the around the fixation cross with respect to the pedestrian hypothesis, the number of pedestrians, and so many more, and also visual factors that are obtained by computer vision methods. So you can imagine we put in a large vector denoted here by X of computational features that we were trying to predict with a nonlinear mapping function, in this case a support vector regression function based on radial basis functions. And we are training this regression function in order to automatically predict these these detectabilities from these input features. As this is a very large vector, we were also doing computational dimension reduction, where we were randomly selecting trained support vector machines in a brute force manner, such that we could get rid of a large number of dimensions and we could reduce the number of features that are responsible for that are responsible for a good prediction of the detectabilities. Now you may wonder what features have remained, and I just want to briefly outline. Have a look please at the paper. It's quite interesting what features remain for such a prediction task. It's actually symmetry. It's the local contrast of the foreground and the background around a pedestrian hypothesis. It's actually the movement of the pedestrian in image plane for the last frame. And most importantly, two features that are dependent on the current human gaze, the distance of the gaze to the hypothesis and the contrast between fixation gaze and the hypothesis, and a few more features. So let me summarize briefly where we are now. So we have determined by an experiment with a distraction task with mental load as a proxy for hazard situation these detectabilities for each pedestrian in the scene. We have established a computational framework that allows us to map features derived from the scene properties that hopefully are reliably available from computer vision systems. We have mapped these features to the detectabilities obtained through the experiment. And now we are equipped, as this function is dependent on the gaze factor, to optimize this function in order to enhance the pedestrian detectability overall in the current scene. So let's see how this looks like in an example. This is a trained regression function. And for an example, of two detected pedestrians in the scene denoted here by these two rectangles, we obtain the following evaluated cost function, which is basically the sum of these two regression functions applied to these two hypotheses. Now we need to find, as this function is dependent on the gaze, just the maximum of this output, and you get this location suggested by our computational framework. This is a nice interpretable example where not the gaze is directed, for example, to the mean location of these two hypotheses. It actually is distracted more towards the less visible pedestrian in this case. So let's see whether this approach overall owes us an improvement for the visual perception of the scene. So I give you a few statistical evaluation measures. We did a second experiment with a strained cost function that can predict these detectabilities. The two conditions were random fixation crosses, and in comparison to that, the optimized predicted fixation cross. We did this evaluation based on our responses we obtained by the subjects, and could show that the performance, the perception performance, significantly improved with respect to the random control and to the optimized control. Furthermore, the false positive rates, which is wrongly labeled boxes by the observers, remains the same, which means that the task performance was not influenced by these two control conditions, but actually that we just improve with this kind of task the perception performance. Maybe less interesting is that the secondary task performance also remains the same, the distraction task between these two conditions. So I want to use the last minute for a little discussion of what we have presented here today. So we extended the detectability concept to more ecologically relevant scenarios, dynamic scenes. What we have to say is that we need really a reliable computer vision framework that detects pedestrians. We're currently thinking of also how to deal with false detection hypotheses. Robust driver monitoring to detect a hazard situation, which is out of the scope of this presentation, might be sufficient. We used videos as surrogate to natural driving situations, and it seems under these laboratory situations that we can improve perception performance, but a final validity needs to be shown really in the field. Other promising features, but that were not available through the database that we were using, are, for example, the ego motion state of the observer of the car and what is probably felt by the driver. Human poses of pedestrian, we were just looking at boxes of these pedestrian, the gaze of a pedestrian, social cues. I just want to show this in this image, what we have been working on. We are trying to provide new databases that actually takes a human pose into account, where people were wearing these inertia tracking suits below the clothes. We look currently on the interaction of more complex social behavior features, the interactions of pedestrians and crowd. We are looking on the gaze of potentially human drivers based on 3D depth sensors. And likely it would be interesting to investigate also the study more in an ecologically relevant situation like simulations in virtual reality. And also what I was trying to promote in the beginning, exploit other sensors that are outside the visible spectrum of the human observer that could be used for enhanced predictions of these predictabilities under more difficult visibility conditions. And last but not least, also we need to think about how to visualize such optimized prediction crosses in a multimodal fashion to the driver. The proxy here was now this fixation cross, as you have seen, but other things like acoustic cues would be feasible solutions as well. So I hope I could convince you a little bit with this concept, and I would like to thank you for your attention and happy to take questions.
Thank you. We have time for one or maybe two very quick questions. Why don't we go down here again?
This one.
Use that one. Use that one.
Well, it should be a short one. You have talked about vision and vision detection, but this is mostly a concept where you have photographic analysis.
For what?
Whereas photographic, so like you have a photo and you analyze the picture. So, for instance, as you acted like Sancho Panza there on the last slide, it would be hard to detect what you were going to do next. And whereas that is an important issue. So instead of just having a visual analysis, have you ever thought about motion analysis? Because that's a much clearer and better basis for decision making, what will happen next.
You mean motion analysis of the scene?
What is?
You mean motion analysis of the scene? Yeah, this was included here in this presentation.
Thank you.
I showed you we were looking at, the protocol I showed you indicated static pictures, but actually these were sequences of images.
All right.
And the motion of the pedestrian actually was a feature that we were looking at if it is a critical feature for the prediction of the detectability. It's included. And actually it's a major contribution of this talk today.
Yeah, no, I think motion's a key feature. Maybe I can just ask one last quick question.
Sure.
So you've measured these different features that sort of attract the eye and the focus of attention. I'm curious to know how much driver-to-driver differences there are. Is there a wide difference between drivers, what they pay attention to?
Let me answer this a little bit different. I mean, this prediction framework was not based on an individual basis, but it summarized the response behavior of all people who contributed to the calibration of the system. So more or less, there were some differences, of course, but I showed you just the average result, and it would be interesting to rule out factors such as age and disabilities, whether people perform in these tasks differently. But turning this around again, we could put this again as a predictive feature, like how old is the driver, into the predictive framework.
Right. Okay, great. All right, let's thank the speaker one more time. Thank you. Okay, our fourth talk this morning is by Marcus Obst, and he's going to talk to us about multi-path detection with 3D digital maps for robust multi-constellation GNSS, INS for vehicle localization. So Marcus.
So, thank you for the introduction. Good afternoon, ladies and gentlemen. Welcome to my presentation about reliable vehicle positioning in urban areas. First of all, before going into the details of the presentation, I want to thank my colleagues directly contributing to this work. There are some terms inside of my title I want to briefly explain at the beginning. So first of all, the goal of the presentation is to have some kind of reliable positioning. You have maybe seen in the first talk of today by Stephanie that there are now many other applications out there, or at least under investigation, where people are relying on a good positioning to build, for example, some kind like a collision avoidance. And I think most of you agree that reliable positioning means to have an accurate position estimate from our algorithm. This means we want to be as close as possible to the truth in reality. But moreover, there are other aspects of positioning. For example, we want to have a really large availability of the positioning solution. And maybe as important is the integrity concept. So we need some measure to decide if we can trust inside the solution which was given or which resulted in our algorithm. And last but not least, we want to have this ready in mass market applications. This means we want to have a low-cost approach, maybe. And this is what the presentation tries to contribute. We want to go in that direction to provide such a positioning. Another term inside of the title was GNSS. Maybe some of you are not familiar with this term. It means Global Navigation Satellite System, and GPS, as you might know, is maybe the most prominent representative we have out there at the moment. And inside this work, we investigated what is happening if we just take 2 of such systems for the positioning. And this is then called multi-constellation GNSS positioning. So simply taking all available systems which are maybe working here in Europe. In the future, we will have Galileo as well, so maybe by the end of this year, there will be 4 additional satellites which we can use for positioning. Before coming to the real core of the presentation, the multipath detection, just some basics about GPS or GNSS positioning in general. So normally, GPS positioning means that we have several time-of-flight measurements between the satellites in space and our receiver antenna at, for example, mounted at the rooftop of our vehicle. And these measurements are called pseudo-ranges. Here's just a simple model in this equation where you can see that the real distance between the satellites in space and our antenna, indicated by R, have to be, there are some additional terms which we have to consider. For example, we have delays caused by the propagation down from space to Earth, and we have things like clock errors. For example, really important, due to the unsynchronized clock of our local receiver, we need to solve or account for the clock offset on Earth compared to the clock satellite system in space. And that's one formulation of such, one common formulation of such a pseudo-range, a one-dimensional measure. Typically, in the simplest case, what we want to do, if we do GNSS navigation, we want to estimate a 3-dimensional position on Earth of our antenna, in this case indicated by X, Y, Z. And as said before, we have to solve for the local clock bias or offset as well. So it's the simplest task we can imagine. If we have at least 4 of these measurements available, we can simply just solve the solution. Of course, more is better. We can do some kind of redundancy checks, nonlinear least squares estimation, and this yields us a so-called GPS, or in this work, maybe better called a GNSS fix at the end. So we're taking several pseudo-ranges, put them into some estimator, and get a position fix. That's the basic of GNSS GPS positioning. But what happens if we now go to challenging areas like, for example, indicated on the right bottom? In dense urban areas, it may happen that we do not have a direct line of sight between our antenna and the satellites. And now 2 things can happen. It may happen that you do not receive the signals at all. That's easily to detect because you do not receive them. And maybe the worst thing is just to receive the signals by reflections as indicated in the upper left image. You can now see that this additional amount introduced by the reflection will cause some kind of bias in the final position estimate. So if we do not consider this additional amount compared to the white arrow, we get a biased and offsetted position, and that's not what we want to have. So it's some kind of unmodeled error. It's an outlier. So one possible extension could be, for example, to extend our model with some additional term indicated here, delay introduced by multipass. The problem is, at least as we realized, that with such a rough model of your environment, it's really, really hard to exactly estimate this additional amount. Though, therefore, what we propose in this work is to use or to build up a representation of your environment around your antenna online, which can be used as a simple ray tracing test. And from the result of this ray tracing test, we want just to exclude potential measurements. So that's the idea. let's look how we want to create this environmental model. It should be really easy. That was the initial goal of this work, to have an easy representation, a low-cost representation, which can be calculated really fast. We are taking different kind of digital map data, therefore. For example, first we need a street map from which we extract the building layouts in our surrounding. So in this case, it was OpenStreetMap, so we just took the layouts of the building from the map. Then we added some kind called digital terrain model. This is the elevation of the Earth surface in respect maybe to the street level or to the ground floor of your buildings. So from these information, we get the footprint height of our buildings. So inside the layout building, we are now checking this map for the elevation data. And the same is done with another source of information, the digital elevation model, which now gives you the height of the Earth surface, including buildings and, for example, vegetation. So from these three information, we can now create a really cheap representation of our surrounding, which then will be used inside the positioning algorithm to test for potential multipath affected measurements. So just to have a look, to give you an idea of how this may work, here you see the hometown of my university. We are driving inside the city center. The green lines indicate now the predicted pseudo-ranges, so what we normally will measure from our GPS or GNSS receiver. And you can now see that at every time step we are checking if some of these measurements or pseudo-ranges can be directly received or not. So that's all we get from the model. Okay. Let's go on. There's one problem with this solution. I told you we need at least 4 measurements to make a GPS fix or a GNSS fix. And I also told you that we propose to exclude outliers. And it now may happen that we are excluding too aggressively, which then would mean that we efficiently lower availability of our solution. That cannot be the final result. And therefore, in this work, the idea was just to use all available GNSS systems so that we have a larger number of satellites, and so we can be more picky about choosing which of these, for example, say 10 measurements which are available at the receiver might be the 4th or the 5 best. So that's the idea. Other approach would be, for example, to do tightly coupling where we can lower the number of required measurements for positioning. This was done in another work shown this year. So let's look how we will integrate it. I told you that we want to do vehicle positioning. In standard vehicles, you nowadays have many of sensor information available. In this case, for example, the odometry and the velocity and yaw rate measurements from your in-vehicle CAN bus. So we are taking these measurements and want to combine them with the GPS or GNSS position fix. Therefore, we use the base filter, in this case a loosely coupled implementation, which means fix plus odometry measurements. The filter was backed up by a motion model of the vehicle, so we can account for the physical constraints, like you cannot have infinite acceleration or something like that. So it's another step to have a more stable position estimate. And now we normally put this information inside this algorithm. This is more or less standard. The question is, how is the multipath detection included? You can now see here that we need to have a low-cost single frequency receiver, for example, providing pseudo-ranges of different satellite systems. We directly put the measurement set at each time step to the multipath detection. This is fed to the least squares estimator, which directly yields the GNSS fix we are using inside of our algorithm. So just for the record, it was a base and unstandard Kalman filter. How did we evaluate our approach? We did some urban trails, so where we have large buildings and a decreased availability of satellite signals. Then for each or for different combination of algorithms, we evaluated the calculated position, the estimated position, against the ground truth, which was available from our prototyping vehicles here. And furthermore, we were also checking how often the present error, which was generated by the algorithm, is inside or outside of the estimated confidence interval or the covariance, which is coming out from the Kalman filter or from the Bayes filter as well. So we can judge how often we violate the promised confidence interval, which is, I think, a really important point. We saw in the first talk this morning that the probabilistic modeling of information and fusing seems to be really important, and exactly this information are generated by the algorithm. We have a mean and we have a measure of how we can trust the information. So just some short empirical results as appetizers for the paper. Maybe the first thing we did, we needed somehow to validate our model. So in this case, we simply went through our city and compared the detections of the multipass model, of the 3D model, against some kind of high-performance receiver, which internally also does multipass detection. And then we compared if our results is more or less, yes, the same or not. And you can see, especially at the beginning of this sequence I present here to you, that we have many, approximately 5 false positive detections. This means that we are excluding too aggressively. Maybe our models, our building models were wrong, they were too big, or they were a little bit too near by the street. Yes, that's a problem, you can see. But at the end of the sequence, maybe the model was more or less correct, so we came to the same results as the high-performance receiver with internal algorithms. This was the first step. And then, of course, we wanted to look at the positioning error and at the performance of the estimated position or vehicle state information. This is just for a comparison, so it's a standard algorithm, just loosely coupled, GPS and GLONASS, inside a multi-constellation fix. And we see here that we, in most of the cases, so the blue line is the positioning error, which was present, 2-dimensional, and the red line is the estimated 3 sigma interval, which means approximately normally you should be in 98% and 89% of the cases below this error bound, below this red error bound. And you see that this is not the case. So we underestimated the problem. And this is maybe, or not maybe, this is of course in this case due to the multipass scenario. So there was no multipass detection included. Just taking all measurements, no matter if they came in via reflections or not. Now let's look at the enhancement for the same situation. So now we just put in the multipass detection from this simple, roughly estimated 3D model, and you can now see that our positioning error is, I would say, probably bounded by the estimated covariance of the same algorithm. So it's all done in a probabilistic manner, nothing special. We put all information inside the algorithm with the additional step of deciding if something may be multipass or not. At the beginning of the sequence, you now see again there was some error in the building models, which means we excluded too much satellites, somehow meaning that we created a worse GNSS constellation. Therefore, our algorithm does not trust the own position so much at the beginning. Okay. These were just some results. Please go to the paper. You will find more figures. And I also provided some videos you can find at the URL at the bottom of the slides. I think, or we think, the simple approach yields a reasonable benefit. So you can just take available data, create the maps around you, and you get an improvement in the positioning error. But maybe the most important, we were able to lower the risk of violating your integrity interval. And I think this is really important. And furthermore, the algorithm seems to be, or is able to be used generically. This means we can use it with GPS, GLONASS, and even with Galileo in the future. And calculations can be done in real time with low computational and even power consumption constraints. So thank you very much for your attention. I would be glad to answer your questions.
Thank you. Okay, we have time for a couple questions. Any questions for our speaker?
Yes, I have a question. I know very well this problem because we do exactly the same at IV' in France. Do you have problem of stability?
I'm sorry, just can you indicate where you are that I can speak
Here.
to you a little bit?
I'm here.
Ah, sorry.
Okay, so my question is, do you have problems of stability in your algorithm? Because
Yes,
I guess that you are using somewhere the position estimated to compute the elevation of, a critical elevation in the azimuth of the satellite. So what is your experience about this?
Okay, so thank you. I think you gave a presentation yesterday during the workshop on this topic. So, and it's really closely related. So, for example, the question is, you need some kind of foot point from which you are making the assumption, I guess that's maybe the question, if a satellite is visible or not. And what we did here, I didn't show you in the slides, you need to consider the estimate of your base filter before doing so. We do not just use the mean of our estimate to check, we are in fact using the whole area of the probable density function to check. So, for example, if you imagine a particle filter for each particle, we are then doing the ray tracing test to check if from the unknown position, for example, we may generate different results. So this is how we solve the problem somehow. For example, also driving into buildings is a real problem because then you estimate no satellite should be visible. Therefore, map matching, at least for the road, is necessary. I hope this answers your question.
Okay, one more question. Well, why don't we go down here if we can?
It seems that
Microphone.
after 10 to 15 seconds, okay. Right. It seems that after 10 to 15 seconds, your model is improving or the results are becoming better. Is it because the motion estimation is
No,
coming?
So you are, for example, asking maybe about this, why it is getting better?
Yes.
I tried to say that by first, for the same sequence, we tried to validate if our model is correct, if the 3D model is correct. And you can see that the model is not correct. It's generating too much false positives. So we excluded too much unnecessary satellites. So for example, here in this case, we maybe only have 4 satellites used for the positioning. And this is why the trust inside our solution is so bad at this moment.
But is it due to the fact that it is in the beginning of the test?
No, it has
or
nothing
is it
to do
just
with the beginning.
incidentally at that point in
Exactly.
the
I just cut the sequence out of a drive, so it's not something like when you go down. In fact, in this algorithm, the covariance is really dynamic. It really depends on how your model says, no, you cannot use these measurements. So the number of measurements is not static. That's the reason why we have such a dynamic covariance, not some initialization process.
Okay, thank you.
Okay, I think at this point we will go ahead and call it all finished. So again, thank you for the speakers. We had a great session.